Hello everyone, welcome back to my channel. Today let us talk about the quantum numbers. Now what are quantum numbers? Quantum numbers are regions in space where electrons can be found. Now when we talk about electrons, these are the negatively charged particles, okay, that are located outside the nucleus of the atom. So let's draw some model of the atom. Okay, so here's the nucleus of the atom, which is composed of proton and of course the neutron, which is a neutrally charged particle, or meaning to say a particle that has no charge. Now, around the nucleus of the atom are this what we call electron clouds. Okay, so these are what we call electron clouds. Okay, particularly is found outside the nucleus of the atom where the energy levels, the sublevels, and the orbitals are located. Okay, so these are the portions where electrons are specifically located. Now, in the model of Schrödinger, okay, he called this model as the quantum model. Okay. Now, in his quantum model, there are four, okay, quantum numbers. The first one is this what we call the principal, okay, quantum number, which has a symbol of small letter n. The values of principal quantum number ranges from n equals 1, 2, 3, 4, 5, 6, and 7. Okay, so those are the principal quantum numbers. Well, the second quantum number is this what we call angular momentum. Okay, so angular momentum, or somehow it is called the azimuthal quantum number, and its symbol is small letter L. And this angular momentum has values ranging from 0 to n minus 1, wherein the value of L in here for S is 0, for P is 1, for D is 2, and for F is 3. Okay, so what does this angular momentum or azimuthal quantum number tells about? Well, this one describes the shape of the orbital. Okay, so example for the S orbital, its shape is somewhat like, of course, spherical. Okay, this is what we call the S shape. How about the P? The P has a shape like this one. And for the D orbital, it has a clover leaf shape. And a much more complicated clover leaf shape determines the orbital of, or the degenerates of, the F orbital. Okay, so these are some of the examples of the shape of the orbitals. Okay, now let us proceed. Now let us proceed to number 3. Okay, so the third quantum number is this what we call magnetic, okay, quantum number, which is a symbol of M sub L. Now, this is really very dependent on the value of the angular momentum. Now, what does this magnetic quantum number means? Okay, so this describes the okay, the orientation, no? Okay, so it describes the orientation of the orbital's angular momentum within the specified sublevel. Now, let's go back to the angular quantum number or the azimuthal quantum number. If you can still remember, the value of S for the angular momentum is 0, for P is 1, for D is 2, okay, for F is 3. Now, the S orbital has, the S sublevel is composed of one orbital only, okay. The P has 3 orbitals. Okay. The D has 5 orbitals. And the F has 7 orbitals. Okay. So each of these sublevel has a specific number of orbitals, and the electrons found in each orbital has that's what we call orientation in space. Okay, so whether they are found in the first orbital or the second orbital or the third orbital. Example, for the p orbital, it has px, okay, it has py, and it has pz orbital. Okay, so if we will determine the orientation in space of each electron in a specific orbital, it is best to know the magnetic quantum number of each of these um, electrons. Say for example, for the magnetic quantum number of the P sublevel, it has -1, it has 0, and positive 1. So in here, you can identify whether an electron is found in the px, okay, orbital, in the py, or is it present in the pz orbital. Okay, now let us proceed to the fourth one, which is the continuation of the magnetic quantum number. That is what we call the spin quantum number, which is a symbol of M sub S. And the values are positive 1/2, which is paramagnetic, okay, and it has a value of negative 1/2 if it is diamagnetic. Okay, so what does this diamagnetic and paramagnetic mean? According to the Pauli's exclusion principle, okay, In a given atom, no two electrons can have identical values. Meaning to say, each of these two electrons have their, of course, different set of quantum number. Meaning to say, one can be paramagnetic and the other can be diamagnetic. The electron also may spin clockwise. It is paramagnetic. If it spins counterclockwise, meaning to say the S here is -1/2. Okay? Now let's give some examples. Okay, so let's give some examples of how to identify an element using, okay, set of quantum numbers. Okay, so let's say, for example, the n is equal to 3 and the azimuthal or the angular momentum is 1 and the m sub l or the magnetic quantum number is -1 and its spin quantum number is equal to +1/2. Okay, so let's identify the the element. Well, the element is in the third energy level. Meaning to say, if we will draw a model of an atom, the outermost electron is found in the third energy level. So this is what we call the n equals 3. Now, its angular momentum is 1. Okay, if we can still remember, the angular momentum here for S is 0, for P equals 1. So therefore, the angular momentum is 1, meaning to say the electrons are found in the P sublevel. Okay, so this is found in the P sublevel, particularly in the -1 orbital. So let's draw, since it is in the P sublevel, let's draw 3 boxes in here that will represent the orbitals of the P sublevel. So this is -1, this is 0, and this is +1, meaning to say that is the Px, the Py, and the Pc. Now let us distribute the electrons. In here, we can identify based on this value here, which is +1/2, that the electrons are paramagnetic, meaning to say it is in a clockwise spin. Okay? Now, let us draw the spin, the electrons in here. Okay? So the electrons in here are, of course, distributed on the P sublevel. So let's distribute the electrons one at a time. Okay, so electron distribution must be one at a time. Now, so let us distribute first the upward spin. Okay, since it is positive 1/2, meaning to say the only orbital that has an electron present is this one. Okay, because of the positive 1/2 thing or spin quantum number and negative 1 ml. Okay, so let's count the number of electrons on the p sublevel, particularly in the px orbital. That is equal to 1. So therefore, we can conclude that the last orbital or sublevel, is in p sublevel. Okay, or the last orbital is found in the p sublevel, particularly in the third energy level with only one electron. Okay, so what we're going to do is to distribute its electrons using the electronic configuration. So let's start here as 1s2, 2s2, 2p6, then 3s2, and 3p1. Okay, so it's in the 3p1 sublevel. So let us count the number of electrons. This is equivalent to 13 electrons. And if we will check it on our periodic table, the element that has 13 electrons is this, what we call aluminum. Okay, so therefore, the element that has this set of quantum numbers is called the aluminum. Okay, so let's proceed to the second example. Okay, so let's say, for example, the set of quantum numbers is equal to n equals 4, the L is equal to 2, the ml, okay, its sum m sub L is equal to 0, and the m sub s is equal to the negative 1/2. Okay, so in here we can conclude that it is in the fourth energy level. And from the value of azimuthal quantum number, okay, so let's again review. S is 1, 0, P is 1, D is 2, F is 3. So therefore, if the value is of L is 2, this is found on the D sublevel. Now, from this information, we can conclude that there are 5 degenerates in this D sublevel. Okay, so therefore we'll draw 5 boxes in here. These are what we call the orbitals, okay, which is used to draw the orbital diagram of electrons. Okay, from the value of D, it ranges from -2 to +2. So therefore, this is -2, -1, 0, +1, +2. Okay, so this is already 1, 2, 3, 4, 5. Okay, so let's delete this one. Next thing is, let us distribute now the electrons one at a time. Again, one at a time. So, since it is diamagnetic and the angular momentum, the magnetic quantum number is 0, let us distribute the electrons up to here. Meaning to say, the electrons in the 0 magnetic quantum number is diamagnetic. Meaning to say, the spin is counterclockwise. It's composed of 2 electrons. So let's distribute the electrons one at a time. Okay. Now let's go back with a downward spin. And there you go. Okay. The 0 is already full of electrons. So let's count the number of electrons. 2, 4, 6, 7, and 8. Okay, so there are 8 electrons in here, and we know that the element is found on the D sublevel with 8 electrons. Now, let us follow the rule which is called n-1, meaning to say the the atom is in the 4th period, and it has 4 energy levels. Now, we will subtract 1 from its energy level to make it 3. Now, we all know already that the energy level of the atom the atom is 3. So therefore, we all know that we will distribute the electrons up to 3d8. So let's start writing the electronic configuration. 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2, and then 3d8. So let us count the number of electrons. We have 10, we have 20, this is 28. Okay, so there are 28 electrons in here, and the atom that has 28 electrons is called nickel. Okay, so this is what we call the n-1 equals 3. So that's all for this quantum number. See you again on our next video.